So we're on page 13 of our notes and just taking a next step at balancing more complex reactions using the half reaction method. Knowing that when Leo says grr, we really start to think of reactions in terms of two halves. If one of the half reaction loses electrons, it ends up on the product side. The other has to gain electrons. It ends up on the reactant side. On our notepad page, we see that we're to fill in the word produces and requires. If one produces electrons, that really is the Leo half reaction. You're going to see those as products. So literally on the right-hand side of our arrow, we're going to start noticing that we're making electrons. Now electrons appear in half reactions, but they do not appear once we combine them back to create a full balanced equation. And over here, if this is the grr half reaction, where reduction means that we're requiring electrons, keep in mind that electrons are going to be written on the reactant side of our half reaction method. And the whole game as we learn how to balance equations is that Leo has to equal grr. Ultimately, when we look at an equation, other than just eyeballing it with coefficients, and we're pretty good at that, sometimes reactions are a little more complex and we can't just spot it by looking back and forth at reactants and products. We have to follow a series of steps that help us balance equations by splitting them in half. We're going to look at a complex reaction and begin to split it into two parts, balance each half of them, and then put them back together. So ultimately, we begin by practicing writing the half reactions. So in a notepad page, we see just a practice in writing half reactions for the following. I see where I have a sodium atom, and I know that it starts neutral, reacting with a chlorine molecule, again, uncombined state, so we know its oxidation state is 0. Over here, we're forming ions of those two elements, a sodium with the +1 and a chloride with a -1. Now, I bet with this simple reaction, what we're able to do is just to eyeball it back and forth and put in coefficients. But the practice here with the simple one is to recognize what are called half reactions. What I notice is sodium going to a sodium ion. To write that as a half reaction, I write sodium atom as no charge, forming a sodium ion with a +1 charge. Now this is the beginning of a half reaction. What I notice is it's not balanced based on charge alone. That so far I have a +1 on one side and a neutral charge on the other. That's just recognition that it's not a balanced equation. What I also notice is chlorine. It started as a 0 and went to a -1. So to begin with, I'll just separate those two half reactions. I'll show chlorine molecule as Cl2, forming the chloride ion as a -1. So in our very first steps of recognizing how to split them apart, we take the balanced or the unbalanced equation we were given and just recognize that one is changing charge from 0 to +1, the other is changing charge from a 0 to a -1. When I think about up here, sodium going to sodium ion, the number of sodiums are the same. I have a number of Na is 1, and over here I have a 1. But to make them electrically balanced, if this is a 0 and it's going to a +1, when I add electrons, remember that makes it become more negative. To bring this positive side down, I can see that this lost 1 electron. And losing an electron is going to form what's called an oxidation half reaction. The loss of an electron is oxidation. So far, we've shown sodium atom losing 1 electron, forming its +1 ion. There's the Leo. In the second half reaction, Cl2 forming chloride, what I recognize is that I can easily place a coefficient, 2 chloride ions, to just simply balance the number of those atoms. If Cl2 needs to be balanced, I have to place a coefficient in front of the chloride. Now over on this side, the net charge is -2, 2 units of a -1 ion. The net charge over here is a -2. Now remember, to balance half reactions, they just have to be the same charge on both sides. Not that they both have to be 0, they just have to be both the same. And what I'm allowed to add, is this whole thing is about redox and it's electron transfer, I'm adding negative charges. So if this side is a -2, to make them both the same charge, I'm going to add 2 electrons to the left-hand side. 2 electrons on this side make both the same net charge of a -2. And I could see that if the first half reaction lost electrons, the second half reaction has to gain, because wherever there's a Leo, there's got to be a Gur. The game now says Leo, the loss of electrons, has to be the same number of electrons lost as electrons gained. In the first half reaction, I lost 1. In the second half reaction, it gained 2. We have to make them the same by distributing to make them equal. So in the first half reaction, if chlorine here needs to gain 2, we've got to go back and double that first half reaction. In other words, we have to distribute a 2 through that first half reaction so that I change the number of electrons lost to match the number of electrons gained down below. Leo must equal Gur. Electrons lost equal electrons gained. So adding them back together. And just as before, when we would simplify, very common we did this with Hess's law, when we would add equations back together and you simplify things that canceled. Think of this arrow as opposite sides of an equal sign. Guaranteed, the number of electrons lost better equal the electrons gained, and they're going to simplify and cancel. And if that doesn't happen, something went wrong, and you just back up and try again. What I'm going to do is add those equations back together, simplifying what I can. Along the way, I'm going to be able to distribute a 2 through that first half reaction. So on the left of my arrow, I have 2 times 1 sodium. I have 2 sodium atoms, no charge, plus, okay, so that's the first half. We're not distributing anything in our second half. The electrons canceled. The only thing left is a chlorine molecule, Cl2. On the right-hand side, distributing a 2 through the sodium ion, 2 units of Na+, and 2 units of a Cl negative. Electrons then canceled. The last thing that we always do, just because it's smart business, you double check, just eyeball, does it indeed balance? 2 sodiums, 2 chlorines, but here's the more important part. Are they electrically the same charge on both sides? The left-hand side, sodium was a 0, chlorine was a 0, the net charge was 0. Over on the right-hand side, 2 positive ones with 2 negative ones do indeed balance to 0. What we've just done, a very beginning simple model of a half reaction method. We took an equation that I'm confident you could have just eyeballed and just counted to double those, but we started that way on purpose so that we could use an easy one to begin with. We split them into 2 half reactions and balanced them based on Leo equal Gur. We combine them back together and just simplify what we can. And the last thing we want to double check, not only are the number of atoms the same, but are they electrically balanced as well? The charge on the left equals the charge on the right. That was our first process of an 8-step process in balancing reactions. Let's take a peek at something a little bigger, something that perhaps you couldn't just eyeball and start counting. I noticed in the note pack, again, I have -1s on the sulfite and sulfate, so I wrote myself a note to say, let's remember to fix the charge from what was typed in the note pack. So I've done that on this overhead slide. Sulfite is SO3 -2. A hydrogen ion is placed in here along with the permanganate ion, and that's a -1. On the product side, we have sulfate, which is a -2, water, and a manganese +2. What we're being asked to do is just decide, what do I do to break those into 2 half reactions? What do we see going together in terms of changing charge? And honestly, I don't really have to start by assigning oxidation numbers to each and every element. What I'm noticing is some common elements from the left to the right. If I'm going to create half reactions, I better place the same elements on 2 halves of the arrow, or it wouldn't make sense to balance. Wouldn't make sense to put sulfite with a manganese and try to balance. They're different elements. So when I begin to think about half reactions, I'm going to hook together like elements on the same side. Here's sulfite forming sulfate as my first half reaction. The manganese in manganese peroxide going to manganese plus 2. The like elements here are the Mn. I'm going to hook together in the second half reaction the permanganate